There's two types of application scenarios we'll cover. The first is related to optimization, and the other is related to rates of change. Let's first look at optimization. Determining stationary points allows us to solve for situations that require us to maximize or minimize some variable. Here's an example. Two positive numbers add up to give a value of 30. Multiplying one of these by the square of the other gives a certain product. What two numbers would maximize the value of this product? So two numbers form the basis of this problem. Therefore, the first thing to do is account for them somehow. You can do that by representing each of them with a different variable. I'll call the first number A and the second number B. It says that they add up to 30, so A plus B equals 30. Then it says that multiplying one of them by the square of the other gives a certain product. We can represent this product as a variable P, so P equals to A times B squared. And the goal is to maximize the value of P. Cool. The first step is to represent P as a function of just a single variable. I'll choose A as the variable, therefore I need to represent B in terms of A, which can be done by making B the subject of this equation, giving B equals to 30 minus A. Then sub it back into the P equation, then expanding this gives, when you multiply out the terms in the brackets by A, you get P equals to 900A minus 60A squared plus A cubed. So now we have an equation with P as a function of A. The idea behind this is, if you were to plot this function as a graph, you want to find the value for which you'd get a maximum, which is a turning point. In other words, a stationary point. As earlier mentioned, you determine a stationary point by differentiating a function and equating that to 0. When you differentiate P as a function of A, you get 900 minus 120A plus 3A squared. Then at the stationary point, this would equal to 0. Then you can divide this by 3 and then you'll be able to solve it by simple inspection. And when you solve it, you get A as being either 10 or 30. So you know two A values at which the graph has turning points, but you still need to determine which of these is a maximum, since you want to maximize the value of P. The way you do this is by determining the second derivative and seeing what values you get when you sub in these different A values. The second derivative would be minus 120 plus 6A. For A equals 10, you would get minus 60. And for A equals 30, you get 60. Then how do you know which of these is a maximum without drawing the graph? You do that by applying the following rule. If f double prime x is greater than 0, then the point is a local minimum. And if f double prime x is less than 0, then the point is a local maximum. The last time we saw something related to the second derivative value being less than or more than 0 was related to the concavity rules. But this isn't linked to that, so don't think about those concave up and concave down rules with these optimization problems. This rule is slightly different, and you should know it as well. What it says is that when you sub in the specific stationary point value into the second derivative equation, if you get a positive value, then it represents a local minimum. And if you get a negative value, it represents a local maximum. For this case, we got a negative value for A equals to 10. So you'd have a maximum at A equals to 10. Therefore, A equals 10 will maximize the value of the product. So A equals 10. We now know one of the numbers, but in the question they asked for both the numbers. And we can calculate B easily using the fact that the two numbers add up to 30. Therefore, by simple calculation, the second number B is 20. And for the very final part of differential calculus, we'll look at the second sort of application, and that's related to rates of change. The gradient of a graph gives an indication of the rate at which the dependent variable changes with changes in the independent variable. If the independent variable is time, and the gradient represents a rate of change. A common rate of change you encounter in your syllabus are those related to motion. For motion, the idea is, if you can model the distance s traveled as a function of a time t, this would be s of t. Then the velocity v could be determined by differentiating s of t with respect to t, which is s prime t. And going a little further, acceleration, which is the rate of change of velocity, could be determined by differentiating velocity with respect to time, which is v prime t. And the first derivative of velocity is just a second derivative of the distance function, so acceleration is also equal to s double prime t. Here's an example which uses these. A soccer ball is kicked off the ground. Vertical height, capital H in meters, of the ball t seconds after being kicked is given by h as a function of t equals to 30t minus 5t squared. Calculate the following. For part A, we need to determine the average vertical velocity during the first 3 seconds. Just keep this terminology in mind. When they ask for an average velocity, they just mean an average in the most basic sense and nothing related to differentiation. In this case, that means the distance traveled over the time taken. You would determine distance traveled by calculating the distance at 3 seconds and the distance at 0 seconds and finding the difference, and dividing this by the change in time, which is 3 seconds. The distance at t equals to 3 is 45 meters, and the distance at 0 seconds is just 0. Therefore, the average velocity is 45 minus 0 over 3, which gives the answer as 15 meters per second. And for these questions, always remember to include the units, because they are important. The next part asks for the ball's vertical velocity after 2.5 seconds. This time they asked for the velocity at a specific point in time, 2.5 seconds. This is known as the instantaneous velocity, and you should know how it's different from the average velocity, because you'll be often asked for both in different parts of the same question. And for the instantaneous velocity, you would calculate it using differentiation, by differentiating the distance function h of t, which would give you 30 minus 10 times t. They want to know the velocity after 2.5 seconds, so t equals to 2,5. And subbing this in gives the velocity as 5 meters per second. For the next part, they asked, what's the ball's acceleration at 3 seconds? As earlier mentioned, you get the acceleration by differentiating the velocity function, and this would just give the answer as -10. Notice that there's no t term in it, so it isn't affected by time. The acceleration is constant throughout, at a value of -10. What does the negative value indicate? A positive value means motion in the upwards direction, and a negative value means motion in the downwards direction. So in this case, that would mean the ball is accelerating downwards, which makes sense because 10 meters per second squared is approximately the value for gravitational acceleration. So the acceleration is 10 meters per second squared in the downwards direction. This is the sort of point where they're testing whether you understand the meaning of the numbers you're dealing with and aren't just blindly plugging numbers into equations and writing whatever answer you get. Just practice lots of motion related questions in class and from past papers to get accustomed to the way you have to think about these sort of questions. Then for the last part of the question, they asked, after how much time will the ball touch the ground again? Again, you have to apply some thought to how this links with the equations you're using. The main idea here is that when the ball touches the ground, the height is 0. So you would just equate the h equation to 0 and solve for t. And when you do that, you get t as 0 or 6 seconds. So which of these is it? At t equals 0, the ball is at ground level because it's just about to be kicked. So it definitely isn't 0 because they asked for the time when the ball touches the ground again. And that would be the higher time value. So it would be 6. Therefore the ball touches the ground again after 6 seconds. And with that, we've reached the end of this incredibly long section. I'll now summarize everything we've covered in this video. First, I introduced the concept of a limit, which refers to the value a function approaches as its input approaches a certain value. So the input value is represented by a, and L is the value that the function will approach as x approaches a. And it's important that the same value of L be approached from both the positive and the negative directions for it to be considered a limit. Otherwise, the limit at that a value doesn't exist. Then I showed that to determine the gradient at a point along a curve, you could determine it using this equation, which uses the basic calculation involved for calculating a gradient, but makes use of this h term, which represents the difference between 2 points, but then for a single point, h would be 0. So by applying the limit formula to this formula, you can determine the limit value as h tends to 0. Then I showed you the differentiation from first principles formula, which builds on directly from the gradient at a point formula and is pretty much the exact same equation, except for the fact that instead of an actual value, which is represented by a, in this equation you just have the variable x. So from this formula, you can determine an equation which allows you to get the gradient at any x value on the curve. And this equation is known as a derivative. And by applying this formula to various different cases, some general trends have been observed, and from that some rules were derived that describe what derivative you get based on what the actual function would look like. And these are the following. The general rule, which says that the derivative of a constant times x to the power of n equals to the constant times n times x to the power of n minus 1. Then there was rule 1, which says that the derivative of a constant equals to 0. And finally, there's rule 2, which says that the derivative of one function plus or minus another function is equal to the derivative of the one function plus or minus the derivative of the other function. Then moving on, I describe the method to determine the equation of a tangent to a curve at a specified point. And it works in 3 steps. You first find the derivative of the curve function, and in the derivative equation, you'd substitute the x-coordinate value of the point to get the gradient of the tangent. And since the tangent is just a normal straight line, you'd use the y equals to mx plus c equation, then the x and y coordinates of the point at which you want to determine the gradient, and the gradient value you just determined in step 2. And you sub these onto this equation, and you rearrange and solve for c, which is the y-intercept value. And once you have c, you can just sub in the gradient and the c value, and you have the final equation for the tangent. Then I introduce a concept known as a normal, which is kind of similar to a tangent, but it's instead the line perpendicular to the tangent at a specified point. And the tangent's gradient times the gradient of the normal will equal to -1. Then I introduce you to the second derivative, which you determine by taking the derivative of the first derivative, and it represents the change in the gradient of the original function. And to sketch a cubic polynomial function of the form ax cubed plus bx squared plus cx plus d, you'd first deduce the general shape by looking at the a value, with the positive a value being a mountain followed by a ditch shape, and then a negative a value would be a ditch followed by a mountain shape. Then you determine the x and y intercepts of the graph. Then you calculate the first derivative of the function, equate it to 0 to get the stationary points, which is the same as the turning points. And by equating it to 0, you'll be able to get just the x coordinates of these turning points. Then to get the y coordinates, you just sub these x values into the original function, and you then have enough information to draw a smooth curve. Then I introduce the idea of concavity, which relates to how a graph's gradient changes as the x value increases, where concave up means the gradient increases as x increases, and concave down means the gradient decreases as x increases. And there's 2 ways to determine it. One is mathematically, where if the second derivative is greater than 0 for a certain x value, then the graph would have a concave up shape at that x value. And if the second derivative is less than 0, the graph will have a concave down shape at that x value. Then there's a visual method of determining the concavity, and that's by using this gradient diagram, which shows the value you get for a gradient at a point based on how the graph looks at the point. So if it's a horizontal line, the gradient would be 0. If it's a vertical line going upwards, the gradient is infinity. and if it's a vertical line going downwards, you get negative infinity. So you'd place this diagram, or you'd draw it in your case, at the very beginning and at the very end of the curve portion for which you want to determine the concavity. And then you see approximately what value would the gradient be at the beginning and end of the curve in relation to how the line falls along this diagram. And by having approximate values for the gradient at the beginning and the end of the graph, it gives you an idea of how the gradient changes as x value increases. And by applying these two rules, you know whether it's concave up or concave down. And lastly, I showed you the two ways in which differential calculus is applied in your syllabus. The first is optimization problems, where the goal is to maximize or minimize some variable. And how you do that is by determining the stationary points by equating the first derivative to 0. And then you determine whether the stationary point represents a maximum turning point or a minimum turning point by determining the second derivative and subbing in the x values of the stationary points you just determined. And if you get a positive value after doing this, then it means the point is a local minimum. And if you get a negative value, then the point is a local maximum. And lastly, we look at rates of change, where it works on the principle that the gradient represents a rate of change, mainly of a dependent variable with a change in an independent variable. And this can be used to model motion and other rates of change. And for motion, if you can represent the distance traveled as a function of time, then the velocity function would be the derivative of the distance function. And then the acceleration function would be the first derivative of the velocity function or the second derivative of the distance function, both of which are the same thing. And that's everything.